Hey everyone, welcome back to Calculus 2. This will be the 19th lecture of the course, and in this section we are going to discuss partial fractions and how they can be used for integration. Okay, and so partial fractions is something you come across probably in like a college algebra course. You maybe picked it up also in pre-calculus, so I'm sure you've probably seen it, and you've probably had some experience with it. If not, don't worry. We're going to kind of go through it, the method itself, a bit here. But this can be an extremely useful technique when you're dealing, particularly with when you're dealing with rational functions that you're trying to integrate. Right. So let's take a look at this. So we'll call this 3.5 partial fractions. Right, so this won't be, strictly speaking, just about partial fractions, but mostly it will be actually, because the actual technique of how this is useful for integration is totally obvious. Really what needs to be kind of taught or learned here is like, how do you deal with partial? How do you do partial fraction decomposition? Because many people are very rusty with it, or maybe some people haven't even ever seen it. It is sort of a more advanced, kind of like college algebra, second semester kind of topic. So some people maybe haven't seen it. All right, but the basic idea here is to take an integral that looks something like this. This is just one example. Something that has kind of a denominator that is, some kind of a polynomial. And it could have, it could be a rational function with a numerator that's also a polynomial other than just the constant 1. And to convert it into something that looks like this. Right, because this over here is not obvious, like what this integral really is. But this over here can be can be accomplished really quickly. This is the natural log of x minus 3 minus the natural log of x minus 2 plus c, right? So this can be done really quickly. But partial fraction decomposition is the act of kind of taking a rational function like this and breaking it up. It's basically what you get when you factor the denominator and then sort of pull everything apart, right? And it's not a trivial operation to do that. It is definitely a pre-calculus topic, but as I said, it's something that you maybe you wouldn't have seen probably in high school algebra. You probably would have caught it in a second semester college algebra and possibly in a pre-calculus course. Okay, so let's review. So what we're going to mostly be doing here is just kind of reviewing how to do a partial fraction decomposition, and then it's very quick and obvious how this benefits integration. Right, so let's review quickly. Well, not quickly, we'll spend a little bit on this. Let's review what's going on with partial fractions. So basically every polynomial with real coefficients can be factored, into linear factors and irreducible quadratic factors. That's just sort of an algebra fact, right? So example, here's an example. X to the 5th minus x to the 4th minus x minus 1. Right, so this guy can be factored as follows. You take x to the 4th, you're going to pull that out of both of these terms, and you get x plus 1 there. And then let's factor a minus 1 out of those terms, and you get another x plus 1, right? And so that means you've got x to the 4th minus 1 times x plus 1, like so, right? And this guy can be broken down. So this is a linear factor, so this one's done. This one can be broken down further into x squared plus 1 times x squared minus 1, and then bring along the x plus 1. And let's see, this guy here can be broken down further as well. So this is coming along for the ride, but this x squared minus 1, that can be written as x minus 1 times x plus 1, right? And then this one, bring it along for the ride. Right, so now these are all linear factors, and this one is what we would call irreducible, right? If we try to factor this down, similar to what we did here, we're going to end up with, we'll end up with, you know, complex numbers, right? Numbers that aren't real numbers. And so we can write this as x minus 1, that's the lone linear factor, and then we've got x plus 1, that's a linear factor, but we've got two of them. And then we've got this quadratic factor, x squared plus 1. Right, so this is linear, this is repeated linear, and then this one over here is quadratic. But notice, this is a quadratic factor that we can't break down any further without sort of leaving the real numbers. All right, and so the idea here is to use this fact to, if this is the denominator of a rational function, to use this fact to re-express the denominator like this, and then ultimately to express the denominator as a sum with each of these factors as the denominator. Okay, so basically this is the idea. This is what we're kind of hoping to accomplish. If we start with something like this, right, nx is some polynomial, and then we have x to the 5th minus x to the 4th minus x minus 1. Right, now here n to the x is assumed to be a polynomial of degree less than 5. Okay, if not, we can always do, you know, run long division, we can do polynomial long division on it and sort of get something different. Right, but basically we want to start with this, and then we know that we just saw that this would be equal to n of x over basically this line here. Right, we just did that exercise, kind of factoring that out. And what we want to do is re-express this as something like this: a over x minus 1 plus b over x plus 1 plus c over x plus 1 squared plus dx plus e over x squared plus 1. Okay, so this is what we mean by a partial fraction decomposition. Okay. All right, so this is a partial fraction decomposition. Okay, let's talk through some of the ground rules of these decompositions, and then we'll do some examples. Okay, so here's what we want to do. So the decomposition of n of x over d of x into partial fractions. Okay, this is kind of this is the sort of how to proceed. Well, we want to first, we want to first make sure that we're dealing with a rational function where the degree of n is less than the degree of d. So if the degree of n of x is greater than or equal to the degree of d of x, we want to use polynomial division to basically get something that looks like this, right? So if you do polynomial division on this, you'll get something like this. N of x over d of x is equal to some polynomial plus a new polynomial n1 of x over d of x. right? And in this case, degree of n1 will be less than degree of d. Okay, so that's kind of the step one. So, if you're dealing with, a rational function where the numerator, you're kind of an improper rational function, then you're going to want to do this polynomial division to get this form here, right? And then steps two, then the further steps will be done to, this part of it, n1 over d, right? Okay, so that's step one. If in fact you have a polynomial where you can apply polynomial division, then you want to do that, right? And then you'll get this new expression, and the partial fraction decomposition will be done on this piece of it then. Okay, it won't work out for you if you're dealing with an improper rational function. Okay, then what's step two? Well, step two then is to factor the denominator, right? And when we say factor, we mean completely factor it, right? It needs to be factored down 100% into linear and irreducible quadratic factors. So, i.e., into linear and irreducible quadratic factors, right? And so those will have a form, right? They'll have the form px plus q raised to the m power, and they'll also potentially, if they're quadratic, they'll have a form of ax squared plus bx plus c to the n power. Okay, so those are the two forms, right? This is linear, this is quadratic. If it's repeated linear, then m will be 2 or greater. If it's repeated quadratic, then n will be 2 or greater. All right, then for each of the linear factors, right, this is what we have to do. It'll have to be written, well, for each of the linear factors, we set up the following. Right, so if I have px plus q to the m power, then I'm going to set up this as the sum of partial fractions. It'll look like this: a1 over px plus q, the first power, plus a2 over px plus q to the second power, plus dot dot dot, plus am over px plus q to the m power. Right, so basically, however many times the factor is repeated, I'm going to require that many terms in the partial, in the sum of partial fractions. Right, so if this is, px plus q to the second power, then just these two will suffice. If there's 3 of them, then I'll need the third. I need the first power, the second power, and the third power. Right, and that's just the structure of the of how these things work out. Okay. All right, and something similar is true for the quadratic factors. Right, basically the same setup, except we actually have 2 constants that we need to identify. So if I have ax squared plus bx plus c, and maybe that's the nth power, then I need to set up the following. It'll be b1x plus c1 over ax squared plus bx plus c plus b2x plus c2 over ax squared plus bx plus c squared plus, and then you can imagine, dot 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 up to bn x plus cn over ax squared plus bx plus c to the nth power. Right, so the same idea as with the linear factors, except here it's quadratic, and so the numerator here is not just a constant like you have with the linear factors. It's actually going to have this form bx plus c. So some constant b times x plus some constant c. Okay, right, so that's the setup. So these are the 4 steps. So you start by, doing the division if you need it. If you don't need it, you can skip this step. If you did do the division, then the further steps will be applied to the remainder, to the term that contains the remainder of the division. Okay, and then you want to factor the denominator complete. You got to figure out what the linear factors are and the quadratic factors, if there are any. And then for each of the factors, linear, you set up this sum, and for quadratic, you set up this sum. Okay. And then, of course, I guess I didn't write it in here, step 5, solve for the constants. That's kind of obvious, I guess, but I failed to state the obvious in this case. Okay, so let's go through an example and see how this works. I'll start with kind of a more chill example. And this will be an example where we just have, single linear factors. We'll work up to the quadratic factors. Let's find a partial fraction decomposition for this guy. 1 over x squared minus 5x plus 6. Okay, so first we'll factor. Well, obviously we don't have to do any division, right? The numerator is a constant, denominator is polynomial. And so we got to factor this, right? And so x squared minus 5x plus 6. Well, some of you may be able to do these things in your head. If you can't, that's okay. You can break this up. So minus 5x is the same as minus 3x minus 2x. Right? You can factor an x out of the first one. You get x times x minus 3. And then the second one, you can factor out a 2, minus 2, and you get x minus 3 again. And so that means you've got x minus 2 times x minus 3. Those are your factors. Right, so this thing factors 100% down into just these 2 linear factors. This is the cleanest possible scenario. Well, the cleanest possible scenario, I guess, would be like a single linear factor, but that wouldn't require a partial fraction decomposition. Okay, so once we've done the factoring, then we need to basically set up the sum of the partial fractions. And so you've got 1 over x squared minus 5x plus 6. Okay, and that's going to be equal to a over x minus 2 plus b over x minus, I'll make this one the 3x minus 2. Okay. Right, so I have 2 linear factors. Each of them is going to pertain to a single, because it's just one linear factor, they're going to pertain to a single term in the sum. So this one is a over x minus 3. This one is b over x minus 2. Okay, and then of course here where a and b are, to be determined. Okay, so we can work this out, right? So basically what we want to do here is you want to get a common denominator on this side. And so let's just kind of go through this. We can skip some steps in a minute, but let's just be really methodical here, make sure we understand exactly how this is all being done. Right, so the common denominator here means you're going to have to basically multiply these two together, right? So the x minus 2 is coming over here, so it needs to be multiplied in the top as well. And similarly over here, you're going to have to multiply the b times x minus 3. Right, and then you're going to get this. Okay, now remember, these are the same, so you can just disregard them. Right, you can think of it as multiplying through by the value of these denominators. And so then you get 1 equals a times x minus 2 plus b times x minus 3. Okay, now what we want to do here is we want to solve for a and b. We got to figure out what values a and b have. I know this is true. These are going to be true for, you can generally assume that these equations will hold for any values of x. And so what you'll want to do is just kind of select values of x that are convenient for identifying a and or b. Right, so For example, to find a convenient choice of x would be x equals 3, right? Because that's going to make this term 0. So x equals 3 means that you've got 1 equals a times 3 minus 2 plus b times 3 minus 3. And so that means 1 is equal to a times 1, right? This is just going to go to 0. Right, so there you've got the first one. Now to find b, you can do something similar, right? Basically, let's go ahead and let x equal 2. All right, so that means you've got 1 equals a times 2 minus 2, right? So that's going to 0, plus b times 2 minus 3, right? So 1 is equal to negative b, so that means b is equal to negative 1. Okay. All right, and so that means we have our partial fraction decomposition. So basically 1 over x squared minus 5x plus 6 will be equal to 1 over x minus 3 plus negative 1 over x minus 2. All right. And so if you were to multiply this through, get a common denominator, and do all of the things, you'd see that this guy here could be would resolve down into the original form. Okay, this is the partial fraction decomposition. And so obviously if you were to integrate this, if you were asked to integrate this, then it would be equivalent to integrating these two simpler integrals. All right, very good. So that's our first example. We'll do a couple more. Let's take a look at the next problem. We'll kind of wrap it into an integration type problem. Let's integrate. Let's see. So it'll be the integral of 5x squared plus 20x plus 6, and that whole thing over x cubed plus 2x squared plus x. Okay, we want to integrate this. Right, so this is a perfect candidate for partial fractions. Right, so we notice here that the degree of the numerator is 2, the degree of the denominator is 3, so there's no division to be done. So first thing we need to do is deal with this denominator. Let's factor this. So let's factor x cubed plus 2x squared plus x. Okay, so we can pull out an x right away. So we get x times x squared plus 2x plus 1. Okay, and this middle one is actually the square of x plus 1. Right, so you might be able to see that, x squared plus 2ax plus plus c squared. Right, so this would be x times x plus 1 squared. Right, so we've got a linear factor, and then we've got another linear factor, but it's repeated. Okay, so this would be kind of like the second scenario that we would encounter. All right, but it's no problem. We set up the equation, and so we have 5x squared plus 20x plus 6. So you have to bring back the original rational function, the numerator and everything. And that divided by x cubed plus 2x squared plus x. And so that's going to be equal to 5x squared plus 20x plus 6, again, the same numerator, over this piece here. Okay, and now here's where we have to bring in our partial fractions. So the form here is going to be a over x, that's for this guy. The single linear factor is going to, have a term equal to a over x for some a, and then the x plus 1 squared, that's a repeated linear factor, right? So it's going to have a b over x plus 1, and there's going to be a second one called c, and it'll be c over x plus 1 squared. Remember, you have to set this up, and there's going to be as many terms in this piece of the sum as there is an exponent on the repeated linear factor. Okay. All right, so what's really important here is, just kind of this part here. right? So what we're going to do, just like before, is, we're going to multiply everything together and get a common denominator of x times x plus 1 quantity squared. Okay? And then that's going to be compared against, it's going to be set equal to this numerator. Okay, so I have 5x squared plus 20x plus 6. Now, this is going to be equal to a times, well, I've already got x in the denominator here, so I just need to multiply by x plus 1 quantity squared. Okay, plus b. Now, b has one of the x plus 1 linear factors, but we need the other one, and we need the x. So we'll have to multiply that times x, and then times x plus 1. And then plus the c, which has the, the repeated linear factors, but just needs the singleton x. Okay, so there you go. Now that's basically going to mean you have a common denominator here, and basically just like before, you can think of this as sort of, you can multiply through by whatever this number is, or by this expression, and it cancels here, and it also cancels over here. Right, so all you're left with is the numerators once you've done this. Okay. Now we just go through and we identify values and ways to identify each of the a, b, and c constants that we need. Coefficients, I guess. Okay, so to find a, let's see. So to solve for a, what can we do? Well, we could notice we could let x equal 0. Right, that won't make this disappear, but it'll make these two disappear. So that's probably the best choice. Right, so over here you get 0 plus 6. So I just have 6 over here. And on this side, I get a times 1. So just a, and then that's 0 and 0. I'll put 0 plus 0 there. Right, so a equals 6. That's good. They won't always be that easy, but that's an easy one. Let's go for c next. To solve for c, what can we do? Let's see. We could let x equal -1. Yeah, if we let x equal -1, then this will go to 0, and that'll also go to 0. It's going to be a little more noise on this side, but that's okay. So we'll get 5 times -1 squared, which is 1, plus 20 times -1, plus 6. Right, and that's going to be equal to 0 plus 0 plus c times -1. So we'll just put -c. Okay, and so that means I've got 5 minus 20 plus 6 equals -c. And so that implies that c is equal to 9. Okay. All right, and then, so we've got that one and we've got that one. Solve for a, we solve for c. Now b will be a little trickier because it's kind of in the middle, right? So to solve for b, well, I mean, we already used x equals 0 and x equals -1. And so x equals 0 deleted, zeroed out these two, x equals -1, zeroed out these two. Right, this guy's right in the middle, so there aren't any convenient factors to use. So, but we do already know 2 of the 3. So what we can do is we can plug in a and c, and then any value of x. So let's write that down. Plug in a and c, and any value of x. Okay. And so let's just use x equals 1. Right, so here I'll get, right, so we can't use -1 and we can't use 0, right? Those are the only two we can't use. Right, but we could use other things like 1. So let's plug in a 1. So if I plug in a 1, I get 5 plus 20 plus 6 on this side. And that's equal to a, which is 6, and then 1 plus 1 squared, right? So that's going to be 2 squared, so that's 4, plus b times 1 times 2, and then plus c, which is 9 times 1. Okay, so we just got to shuffle all these numbers around. Now on this side we get 31. You can see that's 20 and 11. And then I get, what, 24 plus 2b plus 9. And so this is going to be, let's see, 2b equals 31 minus 23, so negative 2. Okay. Yep, and so then that means b is equal to negative 1. All right. Perfect. Okay. All right, so then that means we can rewrite our integral using this partial fractions and see if it makes our lives easier. Okay, so let's integrate. And so we have the original here, 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x. Okay, and we can rewrite that now as the integral of 6 over x minus 1 over x plus 1 plus 9 over x plus 1 squared. Okay, right, so that looks better, right? We can break this all apart, and we get 6 times the integral of 1 over x dx minus the integral of 1 over x plus 1 dx plus 9 times the integral of, we'll write this as x plus 1 to the negative 2 dx. Okay, now all of these things can be quickly done, right? So this is 6 times the natural log of the absolute value of x minus the natural log of the absolute value of x plus 1. And then this one over here will be plus 9 times, now this is like u to the negative 2, right? So that'll be u to the negative 1. So, well, divided by negative 1. So it'll be negative 1 over x plus 1. Okay, and so in summation, this is what you get. 6 times the natural log of x minus the natural log of x plus 1 minus 9 over x plus 1 plus c. Okay, it looks like that. All right, very good. So we've done the two cases that are kind of the, I don't know, I guess I'll say the easier ones, right? What happens when we have a quadratic factor? You know, when we're doing our partial decomposition, we have quadratic factors. Well, let's do an example. This one is already factored for us. So it looks like this: 2x cubed minus 4x minus 8 over x squared minus, well, it's partially factored, not 100%, times x squared plus 4. Right, so you can see in the bottom here, this guy we can actually factor a little bit more. Right, so let's do that. X squared minus x times x squared plus 4 is going to be equal to x times x minus 1 times x squared plus 4. Now, can we break anything down further? No, you might be tempted to try this one, but if you do, you will note that this is irreducible. Right? There's no way to split this this piece down any further. Okay, so then we can set up the factor, or set up the equation. So we have 2x cubed minus 4x minus 8 over x times x minus 1 times x squared plus 4, and that's going to be equal to, now here's the sum, it's going to be a over x for the linear factor plus b over x minus 1 for the other linear factor, and then we've got this quadratic factor here, but there's only one of them, so it's not a problem, plus cx plus d over x squared plus 4. Right, so this is our equation. And then just like before, what we basically got to do is, get a common denominator on this side and that means kind of multiplying terms into the numerator. And when we do that, here's what we get. Right, so the a needs to be multiplied by both of these two, so you get a times x minus 1 times x squared plus 4. The b needs to be multiplied by x and x squared plus 4, like so. And then the c just needs these two linear ones. So okay, so it looks like that. All right, so kind of a handful, but most of these factors we can get off, or most of these coefficients we can identify with relative ease. So we'll start by identifying a. Okay, so to solve for a, what can we do? Well, we'll let x equal 0. All right, the reason we'll do that is because you can see this is b times x, so b times 0, and this over here is c times, well, you've got the x factor here as well. Right, so these will both 0 out in that case. So you get a 0, 0, you get negative 8 equals, and then it's a times negative 1, and then times 4. Okay, and then these two terms 0 out. And so that means what? It means you've got negative 4a equals negative 8. And so that means a equals 2. There's the first one. Okay, let's flip over and we'll try to find b. Let me rewrite the expression here. So I've got 2x cubed minus 4x minus 8 equals a times x minus 1 times x squared plus 4 plus bx times x squared plus 4 plus cx plus d times x minus 1. Okay, all right, just rewriting that same thing. Now we gotta solve for b. What can we do? Well, looking at the b, right, so that's just the linear times the quadratic, so I can use the x minus 1 term to cancel out the a, c, and d. So that will basically mean I'm going to let x equal 1. Okay, and so that means I've got a 2 times 1, so I've got 2 minus 4 minus 8 on this side. Right, and then this is a 0, so that's gone. That one I'm stuck with, so that's going to be b times 1 times 1 plus 4, so times 5. Okay, and then this one over here, this x minus 1 will be 1 minus 1 is 0, so that whole thing is 0 also. Okay, so what do I have? I've got negative 10 equals 5b. So that means b is equal to negative 2. Excellent. All right. Now, what about c and d? Okay, what about c and d? So to find c and d, don't know why I'm switching into lowercase. These are caps. To find c and d, what we'll need to do is we'll need to basically solve, we'll need to set up a system and solve simultaneously, right? So to find c and d, we will set up a system and solve simultaneously. Okay, and so how will we do that? Well, we'll use our values of a and our value of b and some value of x. Okay, some value of x that doesn't turn the c and d term into 0. Right, so set, let's see, what do we find for a? A was equal to 2, b is equal to negative 2, and then we just got to think about an x that'll work here. So we can't use 1 and we can't use 0, so what about negative 1? We'll set x equal negative 1 and see what happens, okay? So we get 2 times negative 1 minus 4 times negative 1 minus 8 over here. Okay. And then on the other side, a is equal to 2, so we get 2 times, and then it's negative 1 minus 1 times negative 1 squared plus 4, so we have to be a little careful here, plus, now b is equal to negative 2, and then times negative 1 times negative 1 squared plus 4. And then we've got the c and d plus, and so this will be c times negative 1 plus d times negative 1 times negative 2. Okay, so kind of did a lot there. Hopefully we didn't lose anything. So let's go through. We got a negative 2 plus 4 minus 8. That's that side. And then over here we've got what? So this is 2 times negative 2 times 5 plus, what do we get here? Well, this whole thing is 5 times 2, so that's negative, so that's 10. Okay. And then plus negative c plus d times 2. Okay, so we're getting closer here. And so all of this is negative 6. And then what do I have here? I've got 5 times 2 is 10, so this is negative 20. Plus 10, and then this is minus 2c plus 2d. All right, so kind of bringing these things all together, what do we get? We get 4 equals negative 2c plus 2d. And so that means 2 is equal to negative c plus d, right? So there's our first equation. All right, now we have to do the same thing, but for a different value of x, because right, we have to set up a system of 2 equations to solve for c and d. All right, so what we could do here is we could use x equals 2. Okay, previously we used x equals negative 1. We could basically plug a, b, and x in and get another system. Right, so when we do that, I'm just going to kind of tear through this one because I worked it out ahead of time. So otherwise it gets profoundly tedious. Basically what you end up with is 0 equals 2 times 1 times 8 plus negative 2 times 8 plus, and then 2c plus d times 2 times 1. Right, this is all with x equals 2. Right, and then so you kind of work that down, and what you end up with is 8 equals 2c plus d. All right, so there's your other one. So now we have a system. And so can we solve this? So negative c plus d equals 2 is the first equation. The second equation is 2c plus d equals 8. All right, so you got this system here. All right, so we can definitely solve this. So let d equal 2 plus c. Then take that and plug it into this bottom one. So that's derived obviously from the first equation, and then you can plug that into the bottom one. So that means 2c plus 2 plus c equals 8. And so that means you've got 3c plus 2 equals 8. And so 3c equals 6, and so c equals 2. Okay, so c is equal to 2, and then we can quickly find out what d is by just taking c and tossing it in there. And so, for example, if you put it here, you get d equals 2 plus c equals 2 plus 2, so d equals 4. Okay, all right. So there we go. Now we have all of the a, b, c, and d that we need to tackle this integral. So let's start back with the integral and see what we can do now. Right, so let's see. So we had the integral was 2x cubed minus 4x minus 8 divided by x times x minus 1 times x squared plus 4 dx. Okay, and now we can write that in terms of the partial fraction decomposition. And we get 2 over x minus 2 over x minus 1 plus 2x over x squared plus 4 plus 4 over x squared plus 4, right? So just make sure this is our a, b, c, and d, right? I kind of broke the cx plus d term apart already. Okay, and then just kind of glancing through here, this is the natural log, natural log. This one we can use a u sub. So u equals x squared plus 4, du equals 2x dx, so du over 2 equals x dx. And this one, let's see here. Yeah, this one is a little bit different. We'll say u is equal to x. This is going to be a u and a, right? This is u squared plus a squared on the bottom. A is equal to 2. Okay, so then of course du is dx. Right, so this is going to be, I believe, arctangent, something like that. All right, let's run through this. So I'll just write it out once more with all of the u substitutions in place. So this will be 2 times the integral of 1 over x dx minus 2 times the integral of 1 over x minus 1 dx plus, now what happens here is just, this is works out perfectly, so this will be the integral of 1 over u du. Okay, just keeping in mind that these are the u's that go with it. Okay, and this one is going to be plus 4 times the integral of 1 over u squared plus a squared du. Okay, so this gets that trig form. And so what do we get? 2 times the natural log of x minus 2 times the natural log of x minus 1. Right. And then this is 1 over u, so that's plus the natural log of u, which in this case is x squared plus 4. And then this is 1 over u squared plus a squared, and so that's the arctangent. So it'll be plus 4 times the arctangent of u over a, so x over 2 plus c. Excellent. All right, so that is what this integral here amounts to, right? So, these examples are, sometimes a partial fraction decomposition is very easy and straightforward. Sometimes it isn't. But as you can see, the integral, this is a complicated rational function, right? This is not something I would know how to do outside of using partial fractions, right? So they are invaluable. For that reason, they're invaluable. So I think that's where we'll leave it. That's a great. We've done all 3 examples, and again, I mean, as said, like the integration side, the calculus side of this partial fraction decomposition stuff is very straightforward. It's basically just rewrite it, and then it's an easy integral to deal with almost always. It's the partial fraction decomposition piece that was kind of we had to review a bit. So. All right, that's where we'll leave it, and we'll talk to you all next time. Take care.